Dear engineers and technocrats, I welcome you all to your favorite YouTube channel Industrial Engineering Guru. Please like it, share it and give feedback through writing comments. After completing today's session, you will be able to explain the sequential sampling plan and design it for given values of AQL, LTPD, alpha and beta. You will also be able to convert sequential sampling plan into acceptance and rejection numbers and draw an OC curve for this plan. Now this sequential sampling plan is a special case of multiple sampling plan where sample size is equal to 1 only. Each time a sample of one item is taken and inspected, then based on cumulative defectives and the number of items inspected, a decision is made to accept the lot, reject the lot or continue sampling, as we discussed for double sampling plan in previous session. Sequential sampling plan is used when accepting or rejecting a lot requires costly or destructive testing. As in this sampling plan, in each sample only one item is inspected. Now, in order to design a sequential sampling plan for given value of acceptable quality level, producers risk alpha, lot tolerance percent defective and consumers risk beta. So these values or these 2 points. So this is the point where a good quality lot is submitted, and at this fraction defective, probability of rejecting the lot, or you can say producer's risk, is alpha. LTPD or lot tolerance percent defective is the fraction defective up to which consumer may allow lot to pass on, and beta is the consumer's risk for the lot quality at LTPD value. Now from these two values we calculate Z1, which is we take log of lot tolerance percent defective to AQL value. G2 is the log to the base 10 of 1 minus AOQ 1 minus LTPD. A is the log to the base 10 of 1 minus beta upon alpha, and B represents log to the base 10 of 1 minus alpha upon beta. So if you see carefully, it is a ratio of LTPD to AQL, which we also used while designing a single sampling plan using Poisson distribution. And when you reciprocate this ratio and subtract it from 1 in both numerator and denominator, you get this G2. A is the alpha is the probability of rejection, beta is the probability of acceptance. So 1 minus beta is the probability of rejection at LTPD level. So here you can have, this is the probability of rejection at LTPD and this is the probability of rejection at AQL level. Similarly, this 1 minus alpha is the probability of acceptance at AOQ level and beta is the probability of acceptance at LTPD level. So after finding these ratios, we have H1, which is the ratio of B to sum of G1 plus G2 values, and H2 equal to A upon G1 plus G2, and S is equal to G2 upon G1 plus G2. By using these values of S, H1 and H2, we get two lines. First line is known as acceptance line, D1. It is Sn, as we have obtained. N is the number of samples, which we will discuss later in more detail, minus H1, this value. Rejection line is Sn plus H2. So these are two straight lines. You see, S is the slope of these lines and these are parallel lines because their slope is same, and this line will intercept y-axis at on the below side at H1 value, and this line will intercept the y-axis at H2 value. So we can plot two lines, rejection line and acceptable line, and these N is your item number inspected, first, second, third and fourth and so on. So in those lines, when we put the value of N for given values of slope and H1 and H2, we get this curve. Now here we have three zones. One is indecision zone, as we found earlier in double sampling plan, or we can say inconclusive zone. And below this indecision zone, we have acceptance zone. And above this indecision zone or rejection line, we have rejection zone. So when we take an item and inspect it, and if the number of cumulative defectives fall on or above this rejection line, then this lot is rejected. If it fall below the or on this acceptance line or below this acceptance line, the lot is selected, and if a point falls within these two lines, then we continue our sampling. Here you also see that when this line is in fourth quadrant where D1 is taking negative values, then we cannot take a decision, or you can say decision is not permitted. Now the acceptance and rejections lines are converted into a table of acceptance and rejection numbers, so that one can compare it with multiple sampling plans. Acceptance number for given sample N must be nearest positive whole number below D1. So we want to convert the previous plan or acceptance and rejections line into acceptance and rejection number. So for this conversion, you should keep in mind that acceptance number for given sample n must be nearest positive whole number. It should be whole number below D1. So it cannot be a negative number. For rejection number calculation for given sample n, the rejection number must be nearest whole number above D2. It should be nearest whole number above D2 and must be less than n. So between D2 and n there can be several integer number, but we have to take nearest whole number above D2. So that would be your rejection number, and acceptance number would be your whole number below D1. So let's discuss how we can have. So let's take an example where S is 0.251, H1 is 1.36 and H2 equal to 1.75. These are arbitrary values we have taken to explain how we can convert this acceptance line and rejection line into acceptance number and rejection number. So when we put the value of S, H1 and H2 and vary the number of items inspected, we get values of D1 and D2. We put S value from here, N value from this side, and H1 and H2 from these values for H1 and H2. So now you see that D1 should be a whole number below this. So we cannot have negative whole number value. So here we put star star, and when this is below this positive numbers, below 1 would be 0, and if the D1 value is between 1 and 2, we take 1, and if it is more than 2, we take 2. Similarly, D2 values are given here. The rejection number would be more than nearest whole number to D2 and below this item number. So here we have any number, or it can be 2, but 2 cannot be less than or equal to 1. So we put here star. Similarly, nearest whole number would be 3, but 3 is not less than 2. So we put here star. And here 3, but it is again not less than 3. So we put here star. Here the nearest whole number is 3 and it's smaller than 4. So we put here 3. Similarly, if you take this case, here the nearest whole number is 5 and 5 is smaller than 9. So 5 would be your rejection number. Similarly, in this case, the nearest whole number above D2 is 6 and 6 is below 14. So we have this rejection number. So we can find for given values of D1 and D2 corresponding to item number inspected, we can determine this acceptance number and rejection number. So you see now this table resembles to a multiple sampling plan. We have taken up to 15 samples, and for each sample we have a acceptance number or a rejection number, and we cannot take a decision up to fifth or you can say third sample here. We have to take more than 3 samples to, and if the fourth sample, if the number of defectives are less than, means you cannot take decision, since here acceptance number is undefined, but you can reject. If you find up to 4, you find 4 defectives, all 4, then you should reject here. But you cannot accept if you get 0 defective up to 4 sample. If you get up to 6 sample a 0 defective, then you can accept it. So here the star means that acceptance or rejection is not permitted. To take a decision about the sample can be made only after, acceptance decision can only made after 6th sample, whereas rejection decision can be made after 4th sample. If you get 4 defectives or combined 4 defectives after 4 samples, you can reject the lot. But if you find 0 defectives up to 5th sample, you cannot accept it because it is not permitted due to negative value of D1. The OC curve of sequential sampling plan can be plotted using these 5 points. At when fraction defective, you know OC curve is a curve between probability of acceptance and fraction defective. Here we have 5 points in sequential sampling plan. 2 are given or 2 are obvious, that at when fraction defective P is 0, probability of acceptance is 1, and when fraction defectives is 100%, the probability of acceptance is 0. These 2 values are given AOQ, this should be AQL, acceptable quality level, where we have AQL, please correct it, AQL, and at AQL we have probability of acceptance equal to 1 minus alpha, as alpha is the probability of rejection at AQL level. Similarly, beta is the consumer's risk or probability of acceptance at LTPD value, and we previously calculated this S value, and corresponding to S, probability of acceptance is given by H2 upon H1 plus H2 or equal to A upon A plus B. So we have these 5 values of P and corresponding probability of acceptance. So using these 5 points, we can draw an OC curve for the sequential sampling plan. Now let's take an example and try to understand what we discussed so far. For a problem where AQL is 0.05 and alpha is 5%, LTPD is 0.20 with beta or consumer risk 10%. We earlier solved it using Larson nomograph method and Poisson distribution table. While designing single sampling plan, we take the same problem for designing a sequential sampling plan, and we will compare the sequential sampling plan with single sampling plan using an OC curve. So as we discussed, G1 value is the log to the base 10 of LTPD to AQL. We put the value of LTPD AQL here. We get G1. Similarly, using these relations, we get G2 A and B. We get these values of G1, G2, A, B, and after getting these 4 parameters, we get H1, H2 and S. By putting these values in these relations, we get the value of H1, H2 and S. We put the values of S, H1 here and get acceptance line, and similarly when we put S and H2 value, we get the rejection line. We can plot these lines and we have this cumulative number of defectives, a graph between cumulative number of defectives versus item number inspected. This is the rejection line D2 and this blue one is the acceptance line. Below this you see that up to 13 number of items inspected, you cannot take a decision of accepting the lot, because here you will get negative value of D1. So at least you have to take 14 sample to make a decision for this plan. 14 samples are to be taken. After that you can accept it. You can reject it earlier, but to accept this lot based on sequential sampling plan, we have to take at least 14 samples. And if after taking 14 samples cumulative defectives are 0, then we can make a decision to accept it. So let's convert it into acceptance and rejection numbers. So you see here up to 30 you are not permitted to accept it. You are permitted to reject it after 4th sample onwards. But to accept this lot, if you get no defective up to 14th sample, then you can accept it. Or if you get more than here, if you see after 10th sample, if your combined defectives are more than 3, then this lot is to be rejected. Now we draw the OC curve for this given problem. We have these 4 points. Fraction defective 0 equal to AQL, acceptable quality level, S, LTPD and 1, and corresponding probability we determine, and we plot the graph. You see this blue line represents the OC curve of sequential sampling plan, whereas this brown line is for the single sampling plan having sample size equal to 40 and acceptance number equal to 4, which we obtained while designing single sampling plan using Larson nomograph or Poisson distribution table. You see, both sequential sampling plan and single sampling plan gives similar OC curve, or you can say that both sequential sampling plan and single sampling plan have similar discriminating power. If you like today's session and found it interesting and useful, please hit the like button, share it with your friends. Thank you. you all for patience hearing, liking and sharing this video and subscribing my YouTube channel Industrial Engineering Guru.